Dear students, I hope you are doing fine and please stay indoor and keep away from this contagious coronavirus. Anyway, welcome to the online engineering physics lecture series. So in this situation, we don't have to fall back in our learning, okay, in our academics. We can still learn. So we'll use this online mode of learning, okay, so effectively. Because in future you may come across with this kind of mode only for learning. So let us try to expose ourselves for this kind of mode of learning. Okay, so in this situation, in this lecture series, the first one will be on quantum free electron theory. So CAE2 portion will start with quantum free electron theory. This is not the entirely new theory. To give lot of background, this quantum mechanics we learned in the module number 1 and classical free electron theory that we learned in the beginning of the module number 2. Okay, so we'll try to club these two. So we know that how this quantum mechanics explain the photoelectric effect, explain the Compton effect. So in the same way it will try to explain the conductivity. So in this segment we will try to understand and we will try to learn assumptions of quantum free electron theory in the beginning. So because we need to know how this assumptions of quantum free electron theory is different from classical free electron theory. And the second one is Pauli exclusion principle. Okay, so how the electrons will be distributed in an atom, because we did not consider this concept in the classical free electron theory. We did not care how the electrons were distributed. And after that, so that is the rule, but anyway it will follow some statistics. Okay, so it is not something like you throw 100 stones towards the apple, so 100 apples will be for, no, not like that. So there will be statistics and we have to follow this Fermi-Dirac statistics. And after that, so the end part is the merits of the quantum free electron theory. Okay, so in this quantum free electron theory, this is the modification made by Sommerfeld on classical free electron theory. Classical free electron theory constructed to explain or give answer why different materials are with different conductivity value. Okay, so now this quantum free electron theory, which was constructed by Sommerfeld, he will simply take the classical free electron theory and he will try to make number of corrections for that. So why did he do that? Why did we need this quantum free electron theory? It is purely because of the shortcomings of the classical free electron theory. It tried to give answers. The theory was elegant. But in science, if the theory doesn't fit with the experimental observation, that theory is wrong, no matter how beautiful is it. Okay, so that is why this quantum free electron theory. So what are the shortcomings that we discussed before CAE1 on this classical free electron theory? One is the specific molar height. The second one is the temperature dependence on the conductivity value. And the third one is the concentration of free electrons on the conductivity value. Okay, so these three experimental observation made the classical free electron theory is incomplete or wrong. So as we had 4 assumptions in the case of classical free electron theory, here too we have got 4. Okay, so we'll try to discuss one by one. The first one is the energy values. Okay, the quantization of energy values. So here you can see the lines representing different energy levels. Okay, and there are gap in between. So this represents the energy values are quantized. It is not continuous. Okay, so the immediately after the first line there is space. Okay, so and these electrons are choosy, and the choosy nature has been revealed in this energy level. And the second one is the distribution of electrons around the nucleus. So of course we had the atomic structure, atomic model, that is Drude atomic model, where there will be positive nucleus sitting in the center and there will be electrons around it. But we did not care the distribution of electrons around the nucleus. So in the case of classical free electron theory, but in here we have to understand how the electrons will be distributed around the nucleus, and that will follow the Pauli exclusion principle. The distribution of electrons in different shells, in different orbits, and it will follow this rule, that is electronic configuration 1s2 2s2 2p6. You might have heard of this. Okay, so anyway, this electrons around the nucleus will follow this distribution law, Pauli exclusion principle. So after that, the another two assumptions, okay, apart from these two, the third one and fourth one will be from the classical free electron theory only. That is, the third one is the free electrons experiences constant potential throughout the metal, which means what? Each and every electrons will experience same potential, okay, throughout the metal. So there is nothing like there is a hump in between. So the road is clear for this electron, for all the electrons. Okay, that is a third assumption. And the fourth one is the all types of Coulombic contractions are insignificant. Okay, it might be electron, it might be electron proton, or it might be proton to proton only. So let us try to understand the first two assumptions, because we discussed about the rest, that is third one and fourth one earlier already. So let us try to understand the first one and second one. So first one and second one, actually I don't have to, or you don't have to worry so much, because we have understood a little bit the quantum mechanics. So in quantum mechanics also we have understood the quantization of energy levels. Okay, in here also the energy levels will be quantized, but why their energy levels are quantized, okay, that we have to understand. So as we well know, any physical objects can have two types of energies, starting with kinetic energy and potential energy. So kinetic energy, it is because of its dynamics, okay, it is because of its virtue of its motion, okay, and the potential energy, it is because of the position and situation of the object. Okay, so for example, so this man has got potential energy because of his position now. Okay, he is sitting away from the earth, so that is why he has got the potential energy. In the same way, if you look at an atom, even this electron, okay, will have the potential energy because it is bound to the nucleus, okay, and it is away from the nucleus. Here also the man is bound to the earth. But man case is quite different with the electron case. So electron is quite different. It is microscopic particle. So that is why it is trapped to this nucleus. So that is why its energy levels will be quantized. Okay. So that is how the quantization will come into picture. So since electrons are trapped to their respective positive nucleus, their energy values are quantized. So electrons will be distributed around the nucleus in differential. It might be K, L, M and N in different orbits. Okay, but how the filling of electrons will happen? Suppose, let us assume that there is a atom and there are no electrons, okay, around the nucleus. So let us suppose, we'll imagine in that way. However, it is not entirely possible physically. Okay, so let us assume that for understanding it. So there is a nucleus and there are no electrons. Now let us add one by one. So I will add, then how the energy levels will be distributed for this electron? This is how it is. Okay, we'll come to that point. So this is how the lines will be distributed. And now if you add one electron, it will occupy the very first line from the ground. So the lower line will represent the lowest energy level, and the very next one will be E2 and E3 and E4, so on. Okay, if you add one electron, it will straight away go to the lowest possible energy level and sit there. If you add another one, if you add another one, then it will go and stay with this electron only. Okay, but we have to notice one thing, that these two electron spin must be different to make them sit in the same orbit, same energy level. Okay, so if you add another one, okay, if you add another one, it will go to the next energy level. If you add another one, each energy level can accommodate two electrons, so that is why two electrons can stay there. And if you keep adding, then two electrons will be added together. Okay, in a different, they will arrange themselves in different energy levels, okay, leaving no single energy level vacant. Of course, there are gap in between two energy levels, but there will not be any energy level left vacant. Okay, and the highest filling is representing using the green line in here, and that will be the Fermi level. Okay, so these energy levels are called as filled energy states, and these lines which are not with the electrons, where the electrons are absent, are called as vacant energy states, and this is called as the green line is representing the Fermi level. What is Fermi level? Then what is Fermi energy? Fermi energy is the energy corresponding to the Fermi level. Okay, then what is Fermi level? Fermi level is the level corresponding to the highest occupied energy level by electrons. Okay, and it can be represented mathematically using EF naught, which is purely depending on the small n. N means the number of electrons in that atom. Okay, if you increase the number of electrons, if you increase the number of electrons, then EF naught will also be higher and higher, and all of them other than this n will be constant. H is Planck's constant, m is the mass of electrons, and pi and 3 and 8, these are all constants, as you well know. Okay, so there is another concept we can think, that is Fermi temperature, TF. Okay, the Fermi energy is EF, Fermi temperature is TF. The temperature at which the average thermal energy of the free electron becomes equal to Fermi energy in a solid. So what do we mean by this? It is simply estimating ourselves what will be the temperature that we need to give if we want to equate the Fermi energy, okay, in thermal means, which means what? Suppose we have got 3 electron volt. So the Fermi energy of atoms in metal, it might be in few electron volts, it might be 3 or 4. As you can see this calculation, EF will be 3 electron volt. If you convert that, if you want to achieve that much energy, okay, using thermal means, which means what? If you equate that to temperature, then temperature will be 34,800 Kelvin. It is a huge number. Okay, so that is why it is a mathematical abstract quantity. It carrying no or major or main significance, okay, in here. So that is how did we get this? How did we get this TF value? It is by EF is equal to K into T. Okay, so and TF will be equal to EF by K, and this TF is nothing but Fermi temperature. Okay, and that will be calculated if you divide the Boltzmann constant by that is Fermi energy by the Boltzmann constant. Okay, so that is how. And what is Fermi velocity? Fermi velocity is the velocity of electrons, okay, which occupy the Fermi energy level. Okay, which means what? If you equate what must be the velocity of electrons to achieve the Fermi energy, okay, then E is equal to half m squared. Velocity means it can be equated to kinetic energy, and we know well the kinetic energy formula. Then EF will be equal to half m Vf squared. Vf is nothing but Fermi velocity. Okay, and if you simplify it for Vf, then you will get Vf is equal to 2EF divided by m whole 1 by 2, whole to the power 1 by 2, sorry. Okay, so this is nothing but Fermi velocity. Now if you increase slightly, what is the temperature? The temperature value, it might be 0 Kelvin to some positive value. Okay, then what will happen to its distribution? That distribution will be, the modification of this distribution can be understood by Fermi function. Okay, and this is from the Fermi-Dirac distribution function, and that is from Fermi-Dirac statistics. Okay, so what is Fermi-Dirac statistics? It will help us to understand the modification of distribution of electrons around the nucleus if you increase or decrease the temperature value. Okay, and the mathematical expression for this Fermi function will be f of E is equal to 1 over e to the power E. E means it is the energy level. Okay, the energy level you are talking about. EF is, as you will know, it is Fermi energy, and divided by K Boltzmann constant, and T is the temperature plus 1. Okay, so now as you can see, this is what the function. Okay, so if you plot f of e versus e, then you will get this curve. Okay, so it is simply we are saying how the curve will be evolved at 0 Kelvin. So if you increase or decrease the temperature, then what will happen? First of all, let us try to understand how the distribution will be for 0 Kelvin. Pauli exclusion principle governed the distribution of electrons around the nucleus in different energy values. So now what will at 0 Kelvin, we should not forget it, at 0 Kelvin, but what will happen to the distribution of electrons around the nucleus in different energy level, okay, when T is not equal to 0 Kelvin. And this distribution alteration can be understood by understanding the Fermi-Dirac statistics. Fermi-Dirac statistics. So what is the statistics and what is Fermi function or factor? Okay, so this statistics will say that what portion of the electrons, okay, portion in the sense how many number of electrons will go to the higher energy level, okay, when the temperature is different value other than 0 Kelvin. And what is Fermi function or factor? This is the mathematical entity, mathematical expression or equation which will allow us to see or evaluate this distribution at a different temperature value. So now let us try to understand. F of E is nothing but 1 over e to the power E. E means the energy value we are talking about, okay, minus EF. EF is the Fermi energy. Okay, Fermi energy is the energy corresponding to the Fermi level. Okay, and that level is nothing but the highest occupied energy level by electrons at 0 Kelvin. Okay, divided by kT, where K is Boltzmann constant and T is the temperature, plus 1. So this is nothing but Fermi factor. Okay, this is nothing but Fermi factor. So now let us try to have different cases to evaluate this function, okay, to see how the distribution will be modified for different temperature value. So now let us take the case 1, where we will try to see the temperature value is 0 Kelvin only. So now let us start with 0 Kelvin only, okay, and E, the value of E we are talking about is less than the EF. Okay, we know well, so we have understood this concept that this will be the filling, okay, and electrons will stay in here. You can see the electrons in here, and until where, okay, the maximum level where you can see the electrons at 0 Kelvin will be the EF. Now we are talking about less than EF, which means what? This portion. Okay, then what will be the probability of finding these electrons in these energy levels? That will be the F of E. What is F of E? F of E is nothing but probability of occupation of electrons, okay, in a particular energy level, okay, particular energy level or particular energy level domain. Okay, so now we are talking about below this EF. So in this situation, let me call it as equation number 1. Equation number 1 will turn to, if we apply this condition, F of E will be equal to 1 over e to the power. Now EF is greater, right? So if you evaluate this, no matter which value you will get, but it will be with negative sign only. So that is why let me call it as minus 6 divided by kT. T is 0. So this denominator will turn to 0 only, plus 1. Okay, so now this can be written as 1 over e to the power minus 1 over 0 is nothing but minus infinity plus 1. So minus infinity can be written as 1 over e to the power minus infinity can be written as e to the 1 over e to the power infinity, and this is nothing but infinity only, so that is 1 over infinity is nothing but 0. Okay, so that is why it will turn to 1 over 0 plus 1. Okay, and that is why this can be written as 1. Okay, if you convert this into percentage, it will be 100%. So which means what? You can find electrons for sure. The probability of finding electrons below this EF in all the energy levels will be 100% at 0 Kelvin. Okay, so now let us see what is the probability of finding electrons just above this EF or above this EF. So let us try to evaluate it in case number 2. So now at 0 Kelvin only. Okay, but now the condition is E is greater than EF, which means what? We are talking about this region. So in this situation, now the equation 1 again, equation 1 will turn to F of E is equal to 1 over e to the power. So now here you see, now E is greater than EF. So in this equation, if E is greater than EF, this whole term will always be positive. So now this will turn to some positive value divided by, and t is 0, so denominator will remain 0, so it will be 0 plus 1. So this will turn to 1 over e to the power, anything divided by 0 will be infinity plus 1. And what is e to the power infinity? Again infinity only. Infinity plus 1 is nothing but infinity only. So this will be 0. 1 over infinity is nothing but 0. So that is why 0, and this is 0%. Which means what? You will not see a single electron just above this EF, okay, at 0 Kelvin. Not even a single electrons can be found above this EF, okay, at 0 Kelvin. So now let us try to increase the temperature value. That is case number 3. Let us try to increase the temperature value. T is not at all equal to 0 Kelvin now, and E is equal to EF, which means what? Let us talk about this particular energy value. We can of course talk about below and above also. So now let us try to talk about what is this EF. Okay, at this point, what will be the F of E? F of E, what is F of E? It is probability of finding electrons in that particular energy level. So in this Fermi energy level, what will be the F of E at T is not equal to 0 Kelvin. Now again equation number 1 will turn to e to the power. Now here you see this E is equal to EF now. So if these two are equal, then it will turn to 0. T is not equal to 0, so it will not be equal to 0 now, but it will be equal to 0. So now here 1 over e to the power 0 divided by some value plus 1, and this can be written as 1 over e to the power 0 divided by anything will be 0 plus 1, and we know well that e to the power 0 is nothing but 1, and there is another 1, and this can be written as 1 over 2, and that is nothing but 0.5, and this is nothing but 50%. Which means what? Probability of finding electrons about the Fermi level at different temperature value other than 0 Kelvin will be 50% all the time. Okay, so let us try to understand this concept graphically. So now if you plot the graph, okay, so as you have already seen it just beside the screen, okay, so I have whatever I am explaining in here, so everything is projected just beside this screen, so you can follow there also. Okay, so this is E and this is F of E, and now let me say this is the first excited level, second excited level, let it be. This will be EF, that is Fermi energy level, and this is the energy level above this Fermi energy. Okay, and this will be 100%, or let me simply call it as 1, okay, at lower than EF value at 0 Kelvin, right? So that is why all energy levels will be 100%, which means all of them are full, okay, until here, and all of them above this EF will be 0, which will sweep along the x-axis. So now if you give different temperature, this is for T is equal to 0 Kelvin. Now if T is equal to T1, which is not equal to 0 Kelvin, now then what will happen? This will be 50%, right? If it is 100%, this will be 50%, or let me simply call it as 0.5. And now the curve will trace this point, this shape, okay. So the missing portion will appear in here, okay. So if you, this is for T is equal to 1, for T is equal to 2, this will be like this, okay. Of course, T is equal to 2, you can say it in here, and this is T is equal to 3, T is equal to 4, and it will go on in that way, okay. So this is how the distribution will be altered with respect to the temperature, okay. So above or below the Fermi energy level. So another concept we have to think is the effective mass, m star, okay, because in the case of classical free electron theory, or so far we just learnt the mass of electron will be constant, okay. Mass of that electron will be constant throughout the process of conductivity, okay, throughout the phenomena of conductivity. So here we need to think what is the mass, what will be the mass in different situation. So what is the situation and how the mass will be different, and how it is different from effective mass. So we'll come to know now, okay. So let us consider a metal where positive ions are placed, okay. So it is nothing but lattice points. So now if you want to see the electricity, that is conductivity phenomena, then you need to apply the voltage, okay, plus and minus or across it. Then what will happen? Electrons will start to move, okay, towards the positive, leaving the negative, okay. So now in that case what will happen? These positive nucleus will try to pull them, okay, so pull them towards it. So that is how these electrons will experience some adversing effects, some inertia to move, okay, move along towards plus. So we did not account this, we did not consider this in the case of classical free electron theory. So that is why this pulling will reduce the momentum of this electron, and that is why instead of accounting there are number of positive nucleus and they are pulling this electron, we will try to increase the electron mass and forget about this nucleus, okay. So the electron itself is heavy now. Instead of considering all the positive nucleus are pulling them, okay, pulling these electrons. So in that case this electron will have the effective mass. So effective mass will be different for different metals, okay, different materials. So if the attraction is more, then the pulling is more, then the effective mass will be more. If the attraction is lower, pulling will be lower, effective mass will be lower. So that is how different metals will have different effective mass, but we did not consider this in the case of classical free electron theory. So that is how it will be advantageous for us to explain the failures of classical free electron theory using this quantum free electron theory. So now the time has come to compare the expressions of electrical conductivity due to a based on classical free electron theory and quantum free electron theory. So if you can see, as you can see that classical free electron theory electrical conductivity expression, that is sigma is equal to Ne square tau divided by m, where N is nothing but concentration of free electrons per meter cube, okay, and E is charge of electron, tau is the mean collision time, and m is the mass of electron. So now m is simply m, okay, so there is no star upon it, okay. So now if you look at the quantum free electron theory, then it is sigma is equal to Na square lambda divided by m star into Vf. Now compare these two. What is changed? In the case of classical free electron theory, instead of tau we have written lambda divided by Vf, and lambda is nothing but the mean free path, and Vf is nothing but Fermi velocity. And instead of m, we have written m star, and m star is the effective mass of electron. So this is the expression for electrical conductivity based on quantum free electron theory, and this expression will explain completely the phenomenon of electrical conductivity of classical free electron theory in here. So now let us see how this quantum free electron theory will account the to address the failures of classical free electron theory in here. The first merit, okay, so that is nothing but merits or success of quantum free electron theory. The first drawback that we come across in the classical free electron theory is the specific molar height. We could not account this, okay, so because theoretically that was a huge value, but practically it was a very lower value, and it was not at all dependent on the temperature. Okay, so now we have got a new expression that will say Cv is equal to 2k divided by Ef into RT. Okay, and R and T, here you can see it is depending on the T, specific molar heat is depending on the T also, and 2k by Ef. So if you calculate what is 2k by Ef, then it will be 10 power minus 4, and Cv will be equal to 10 to the power minus 4 RT. So this exactly matching with the experimental results. So now the temperature dependence of electrical conductivity. So as we had seen in the case of classical free electron theory, experimentally we observed the conductivity value was inversely proportional to temperature, but theoretically the sigma was inversely proportional to root T, where that root T was extra. So that is why the classical free electron theory failed to account it. So in here, according to this quantum free electron theory, we can it will follow some explanations. So that explanation will fix that drawback. Okay, so suppose let us assume that there is a metal and there are number of atoms, ionic cores or lattice points, and if you increase temperature, what will happen? The atom will start to vibrate. Okay, the maximum displacement of atoms will be the amplitude of vibration. Okay, and that amplitude of vibration will be depending on the temperature value. Higher the temperature, higher will be the amplitude of vibrations. Okay, so this vibration will be in 360 degree, okay, in spherically, so in all possible directions. So it will create a vibration sphere. So it is as if you are extending the volume of the atom due to vibration. So it is vibration sphere. Okay, higher the vibration, higher will be the sphere. Okay, the sphere radius will be higher. So now this mean free path will be inversely proportional to this area. Okay, suppose in any way the electrons will experience an area of vibration. Okay, so even though it is a sphere, so because due to which the electron atoms will be vibrating, if electrons comes, it will try to kick it. So if the electron tries to come in other way also it will kick it. So in any way the electrons try to pass across this atom will start to kick. Okay, so that is why you can consider that kicking area, okay, that will be a circle, and that area of the circle will be inversely proportional to mean free path. So mean free path will be inversely proportional to pi r squared. Okay, so and this amplitude is depending on the temperature. Okay, so since this mean free path is inversely proportional to this area, but that area is directly proportional to temperature, so that is why we can say temperature is inversely proportional to mean free path. So since temperature is inversely proportional to mean free path, and mean free path is directly proportional to sigma, that is electrical conductivity, we can easily say that temperature is inversely proportional to conductivity, or conductivity is inversely proportional to temperature. So this is how it will fix this drawback. Okay, so now it cleared that sigma is inversely proportional to temperature. third point is the free electron concentration dependence of electrical conductivity. It was a puzzle because as we have seen, even for our intuition, common sense, if higher the electrons concentration, higher must be the conductivity value. But that did not happen because as you can see, the aluminium and some other material like gallium, they are with higher electron concentration, but they are comparatively with lower conductivity value to the copper. Okay, so copper conductivity value was higher comparing to these two. Okay, so though the copper is with only 1 free electrons per atom. Okay, but so that is why that theory, classical free electron theory, failed to account this. So in quantum free electron theory, we have to consider lambda by Vf parameter and m star parameter also. So lambda by Vf and m star is nothing but the effective mass. The effective mass, you should not consider only the concentration of electrons, you should also consider lambda by Vf and m star. If small n is higher, the electron concentration is higher, then these two will be different value. So these two will compensate so that a particular metal will exhibit lower conductivity value or higher conductivity value. If small n is higher, if m star is also higher, then these two will compensate, so you will get the same value. If lambda n value is higher and m star value is so much higher, then the m star value will be dominating. So that is why sigma will be lower. Okay, and in the same way, lambda by Vf, if it is higher, then sigma value will also be higher. So even though aluminium and gallium has got higher small n value, m star value will be higher. M star value will also be higher. Okay, but it will be lower in the case of copper. So this is how the quantum free electron theory explained completely the experimental aspects which were not completely explained by the classical free electron theory. So that is what the merits of quantum free electron theory. Thank you.